Hello, and welcome back to our studies in physics. In this lecture, we're going to talk about vectors and scalars and make sure we have a clear idea of the distinction between them. So all quantities that we're going to study this semester can either be categorized as a vector or a scalar. So vectors, they require both a magnitude and direction to be fully defined. So when you're talking about anything like position, displacement, velocity, acceleration, forces are just pushes or pulls. We haven't quite gotten there, but we will soon. Momentum, torque, two other quantities we'll be studying this semester. We must give both magnitude and direction to any of these quantities so that we can fully define them. If we just give magnitude, then we've only half defined that quantity. So anytime I ask you on a test, on a quiz, on a homework problem, anything like that, to give me any of these quantities, don't forget that you must give me magnitude and direction. If there is a negative sign, that's going to go with the direction part of the quantity. So the magnitude will always be some positive number, and the direction will be adherent to whatever coordinate system you're using. We're going to spend a lot of time talking about different coordinate systems. All right, scalars are the other type of quantity that we'll be dealing with. They require only a magnitude to be fully defined. So some examples of scalar quantities: temperature, distance, speed, and mass. We haven't actually defined mass yet. It gets the symbol m, and the standard unit for mass is a kilogram, not a gram. So these are the two different quantities that we want to make sure we have a clear idea that the difference between the two. And of course, the most difficult to deal with is vector quantity, because you require both a magnitude and a direction to fully specify it. So how do we graphically represent a vector? So a vector can be represented as an arrow. The length of the arrow is indicative of the magnitude part of the vector. And the direction that it's pointing is going to be identified by the direction that the tip of the arrow is directed. So I will just give this some kind of a symbol A. So this could be a velocity, a displacement, it could be an acceleration of force, whatever you want it to be. When you're talking about a quantity that is a vector, you typically put a arrow over the top of that quantity to remind yourself that that's a vector quantity. So you can just kind of see that this vector is pointing in the first quadrant. If I was to draw a coordinate system at its tail, then you would see that it is pointing in the first quadrant. So this is the tail of the vector, and this is the tip of the vector. What does minus a look like? What if I took a vector quantity and I wanted the negative of it? Which is going to be useful when we subtract vectors. We can add negatives. The negative of the vector is going to be the exact same length, but we're just simply going to take the tip of the arrow and move it to the other side. So this is going to be minus a. So those are graphical representations of some vector quantities. How do we add vectors graphically? Well, there's a couple of different ways we can graphically add vectors. So this is graphical addition of vectors. And by the way, we're also going to be talking about subtraction as well, but we're also going to be using addition when we discuss subtraction, because again, we're just going to be adding a negative. It's the same thing as subtracting. So graphical addition, subtraction of vectors. So let's say I have two vectors. Here's vector A, and let's make this one right here vector B. So what does minus B look like? Again, same length, pointing in the opposite direction. So that's minus B. It's always easy to remember the negative of a vector. So graphical addition, let's say that I want to add vectors A and B. And when I add two vectors together, I get another vector. So we'll call this vector R. R stands for resultant, the resultant of the addition of two vectors. So let's look at the two different ways we can graphically add. The first way is called tip to tail. And that's where you just simply grab the first vector A, and notice that this vector right here can be drawn anywhere I want. As long as I maintain its length and its direction, it is an identical vector. So here is going to be my vector A. And now I want to add B, vector B to it. So now I take vector B and I place it on the tip. I place the tail of vector B on the tip of vector A. So there's vector B. The resultant vector has a tail with the tail of the first vector and a tip at the tip of the second vector. So that is vector R. Notice that's just a graphical representation. The more precise the instruments are that I use, if I broke out protractors and rulers and made these lengths very specific, the closer I would get to a closer estimate for the resultant vector R. But graphical addition and subtraction is still limited to some kind of an error associated with the instruments you're using to measure. So these are just approximations. When we talk about graphical addition, it's just an approximation, but it's sometimes very useful to see. You can see that vector R should be pointing in the first quadrant, and that its angle is probably going to be between 0 and 45 degrees that it makes with respect to the x-axis. Again, I can just put a coordinate system at the tail of any vector to look at what direction it's pointing with respect to quadrant 1, 2, 3, and 4 of our coordinate system, standard quadrants. The other method that we can use is called the parallelogram method. So parallelogram. Okay, so that's where we take vector A and vector B and we place them tail to tail so that they'll form two sides of a parallelogram. Remember, a parallelogram is a four-sided figure with two sets of sides that are parallel to one another. So for example, this is a parallelogram. These two sides are parallel and these two sides are parallel. This is what a parallelogram looks like. So I'm going to take vectors A and B and place them tail to tail. So again, I just lift up vector A and I place it wherever I want it. So here's vector A. And now I'm going to place vector B on the tail of vector A. So tail to tail. And these are two sides of a parallelogram. So now I need a side parallel to this one. And I need another side parallel to this one. So there I've completed the parallelogram. The resultant vector R has a tail with the tail of the two vectors and a tip at the opposite end of the parallelogram. So there's my vector R. You can see that this vector R is the same as this vector R. You have to use your imagination a little bit here. Again, I'm limited with the resources that I'm using, but you can see that they are generally both in the first quadrant, both of them making angles between 0 and 45 degrees. And again, the more precise the equipment I use, the closer and closer I get to a true estimate of vector R. What about subtraction now? So that's the last thing. We have two graphical ways to add vectors. What about subtraction? Well, we're just going to use the same principle of addition, and the book will go through and talk about how to subtract vectors, and you have to memorize a whole different way of aligning the vectors together. And you know, I don't like to memorize all of that stuff, so I just simply add a negative. It's the exact same thing. So now let's say that I want to take a subtraction of two vectors. So let's say my resultant vector, and I'm going to put a prime on this because I want to distinguish it. This is going to be a different vector than this one right here, so I'll put a prime just to distinguish it. This vector R is going to be a vector A minus vector B, but I can write this as A plus A minus B. Now I use the exact same rules, and let's just look at tip to tail to begin with. Tip to tail. And so we're going to take vector A. Again, I just simply lift vector A and I place it wherever I would like. So here's vector A. Okay, now I'm going to place vector minus B on the tip of vector A. So here's minus B. I'm going to pick it up and I'm going to place it right there. So there's minus B. Vector r is the vector that has a tail with the tail of the first vector and a tip at the opposite end, and that's actually r prime to distinguish it. This is a very different vector than this one. So this is the subtraction of the two vectors now. And notice that the order of subtraction matters. In other words, now let's look at a vector r double prime, and this vector is going to be b minus a. So vector r double prime is going to be b plus a minus a. So again, using tip to tail method, we just simply pick up vector b, we place vector b here, and then tip to tail, we're going to add vector minus a. So here's vector minus a, we simply place it right here. And you can see that this is the vector r double prime. Notice that a minus b and b minus a are vectors that have the same length but point in exactly the opposite direction. Okay, so this gives us a nice introduction to what vectors and scalars are, and also how to graphically add with the addition of vectors. One last thing I'd like to note is that there is a slight advantage to using the tip to tail method in that you can add as many vectors together in a tip to tail fashion as you would like. In other words, I could place another vector. If I have vector C that I wanted to add here, I would just add it now, its tail to the tip of vector B, and then D and E, and however many vectors I had, I could keep adding them in the tip to tail fashion. The parallelogram method is limited to only being able to add two vectors at a time. So we'll see you next time for more fun in physics.